So today's topic is discussing some of the different ways that we can convert existing objects into sheet metal components, and more specifically, how to get the flat patterned objects out of them. So I've got a couple different things I want to talk about. Obviously, the first big thing that I do want to point out is Inventor's kind of capability limit, right? And the first big thing to think about is we're working in a brake press type of environment, or a very basic die form type of environment. We can't really do progressive die stamping. We can't do necking operations within the system and flatten those components, at least not yet. We do have some new functionality available to us to help get us some at least basic understanding about how a component might flatten, creating heat maps of that networked flattened component. I'm not going to be talking about those today unless time allows at the very end of the presentation. So when we go through this process, we're thinking about linear or roll form shapes in order to get the flattened profile shapes out of them. And so with that ideology in mind, just some different things that we can look at when we work with parts. So the first file that I want to open up here is just a basic Inventor part file. And in this case, this model has not been created using any kind of sheet metal functionality at all, right? It's just a standard extrusion profile and a shell to hollow out the bottom side of this component. And I have already turned on the sheet metal functionality, but just as a general note, if you are in the 3D modeling tab, at the very end, you should have the convert panel, and within here you can then convert to a sheet metal component. Since I've already done this step, it's marked as convert to standard. Additionally, just as a general note, sometimes this gets turned off if you're not doing this process a lot. So just know that you can re-enable that convert tab, or excuse me, the convert panel to bring that tool back. So one big aspect of this process is the sheet metal thickness definition. If the sheet metal thickness that's defined within your sheet metal defaults is not the same as the thickness of the component, you will run into issues, right? The component will not flatten because it does not see an area that it can use as that thickness value. So right off the bat, the first thing that I want to do in this component is I want to make sure that this shell is utilizing that thickness definition. If you're not familiar with sheet metal, within the part files, there are a number of parameters that get created that utilize that definition. So in this case, that thickness is essentially just a mathematical value defined within the space. Beyond that, the sheet metal default defines where that thickness is marked. So in this case, it's already set to 1 millimeter. And what I want to do is I want to change the shell so that it utilizes that thickness value. So I'm simply going to edit this feature and make sure that this thickness is not an arbitrary 1 millimeter, but is actually pulling the thickness value out of the system. I did that kind of quick here. Edit the feature. So again, that thickness parameter is just there. Okay. In my case, I typed it in, but you could also come over to here, list the parameters, and thickness is always available within a sheet metal component. So now that I have that, if I were to go to my sheet metal defaults and update this value to a new definition, we can see that that sheet metal default is pushing into our parameters, which is then in turn pushing into our features that define this component. So that's going to be one of those critical steps in here. It's not absolutely required. In my case, the values happened to be the same, so it would have worked. But if for whatever reason I want to change the sheet metal definitions, I'm immediately going to run into problems where this part is no longer the correct size. And so it just makes good sense to make sure that the thickness of the material is actually tapped in and utilized within the features that define it. So now that I've got that, the next thing that I need to do in here is I need to start ripping some of this apart, because as it stands, this is definitely not going to flatten, right? It doesn't create a network shape based on what's here. So within our sheet metal tools, we have a number of commands to do this. The first tool that I want to use is our bend command. And as I select the bend command, it will allow me to come in and select locations where I want bend operations to take place. And as I do that, it will put that fold on that corner. Now, in doing that, it's also putting in some of our bend operation remnant material cutaways and things like that. And right now it's set to straight. I may go back in after the fact and adjust some of these just based on how it cuts the edges. Usually it does a pretty decent job though, as far as defining these. Let's cancel that. No, that would not bend there. Whoops. Let's try that again. Bend over here. Okay. So now that I have my first two bend lines in place, I need to cut away everywhere that they're not in use. And so to do that, I'm going to use my corner seam command. And within the corner seam command, in this case, I'm going to be ripping edges away. So I'm going to switch the option to the rip. From here, I can select the edges that I'm not interested in. And by default, it wants to symmetrically rip these edges. But in my case, I can swap this to be, one direction or the other or equal, depending on what my sheet metal fabrication goals are. In my case, I'm just going to cut both of these back and trim that boundary. Now, in my case, this is actually giving me kind of some weird results. So let's delete these out. And then I'll reattach the bend instead. And that looks a bit better. I'm going to edit this and switch this to the tear option to not put a remnant. So we do have some various options depending on the order of operations within this process to get different cutaways within the process. Alternatively, if I get rid of this bend and I rip all of these corners away, all at once, it's going to clean up that boundary all the way around. In my case, I didn't edit the existing one. So edit that and select all my edges. We can get a clean separation between those components. I'll repeat the process on the other side. And then from here, using my bend tool again, in this case, I need to reconnect these two elements. So I'm simply going to select the two outer boundaries. What? Let's do it back. Extend body. Not sure why that's failing. What I was trying to show is that you can separate the entire body apart if you need to. And it might be because I didn't do the tapers first. It's not going to flatten that way because it's got that internal gap. Let's do the bends where the bends are. So we know these bends exist, so we can apply those. That might be the reason why it's failing. I'm doing the order of operations a little bit abstract here to try to force it to make different shapes. But now that I have those bends in the actual radiuses, yeah, that's why. Okay. So it was freaking out because it didn't know what to do with this upper corner. It was sharp. That was not an actual bent corner. So I was skipping a kind of a key step of this, which in this case is, we know we have bent flanges on this upper area, so making sure to select those first to get them done. So the gist of this is if you have a component like this, you want to rip away all the boundaries you don't need apply the bends where the bends exist as, solid objects, in this case, the flanges, and then go back in and create the bends where you have potential gaps that you want to close back up. Now that I've done that, I've essentially cleaned up all of these boundaries. If I did want to push these, push these gaps the other way, so that there's actual overlaps, it would just be a matter of coming into our corner ribs. And again, if I edit this feature, I can push or pull where those corner ribs exist in the model. So in this case, we can see there it's pulled that edge flush over the top. From here, I could go in and close the gap size and put corner radiuses on this model in order to clean up that boundary to help adjust the size of it on the part, so that I've got cleaner edges, no sharp corners at all. So I need to go in and just adjust this one. So edit the feature, push this so it's over the top. And there we go. So at this point, this component had started out as just a base extrusion and a base shell. I've then updated the shell so that it utilizes the wall thickness of our part. And then beyond that, used the combination of the corner and bend tools in order to strip the component down to having the correct bends where I need them, gaps where I need the gaps, and then finally reconnecting edges as I remove them. In doing this, I'll save the part, and I should be able to, in turn, define the A side of the model. What the A side is doing is helping calculate where our neutral axis definition is. It's also defining our bend orientation. So if I wanted to bend these upward or downward, depending on what face I select or what set of faces I select, that's going to dictate that direction. In this case, I'm simply going to pick the outer edge, and it defines that A side on the component. I'll then create the flat pattern network for this object. Obviously, from here, some other things that we could do, if I did need to do any kind of cleanup on this model, I could do so. I can take a look at the bend orientation or bend order of this part and see those definitions in here as well. But that first component is now completed. So the next thing that I want to look at is some other ways to potentially, some other questions or some other things to see potential issues with a model and how to fix them. So in this case, what I want to do is I'm going to simply open up this left part. And in here, we can see that this was made using a number of 3D features to create this part. From here, I am going to convert this to sheet metal. And when you do the convert to sheet metal function, the very first thing it wants you to do is select a face on the model. And what it's going to do is it's going to look for essentially a parallel face to the face you select. And it's going to use that to define the thickness of our model. So in this case here, I'm just going to select the inside wall. And as I do that, it picks up the 10mm thickness of this design. Okay. From here, I'll hit OK. And then in my case, as I did before, I just want to edit this base feature that's defining our thickness and simply adjust this value to use that parameter. Now in doing that, I now want to go through kind of some of the finalizing steps. I know I want this to be my A side. And then from here, when I click create flat pattern, this fails. And it fails because the component does not maintain 10mm wall thickness throughout, right? So it needs to be uniform wall thickness through the entire component. Anywhere that it's not, it's going to fail. So in this case, it can't flatten this zone. So in my case, I'm simply going to undo in order to get rid of the flat pattern. I don't want that in the system trying to update in real time as I'm working on this component. And so in this case, if I take a couple measurements in here, I can see I've got an internal radius here of, in this case, 3mm. If I run a radius on the outside, I can see in here it's got a much different radius value. Let me restart that and reselect it. We can see in here we've got a much different radius value. So what that's telling me is that the offset value is not correct. While I'm doing this, I'm going to simply restart and do a couple more sanity measurements and just make sure, okay, this one is 10 mil, that's good. And here is 12. And so I should have 22 out here, and I'm slightly different. So basically what it looks like is that when somebody modeled this, they tried to model some of the quote unquote taffing or stretching of the part, the elongation caused by the bends. And we don't want that, right? We're not going to model that inside of our sheet metal components. Again, we want to make sure that they are uniform thickness throughout. So in this case, I'm going to go find those features and try to clean them up. And in this case here, we can see that, yeah, there is definitely a dimension in here. So we're just going to delete that out and make these concentric. Let's do the other way. Adding this over constraint with sketch. This plus that. There. So that cleans up the fillet radius there. In all reality, I could have also added in the tangency to this. I'll repeat the process on this side. So this component as well, this shape is just not symmetric or not uniform, concentric in the model. So we're just going to delete that out. Add the concentricity. I'm not sure if I'm getting that error all of a sudden though. This plus this. Now, in all reality, I'm selecting the existing dimensions inside of these sketches. If I really wanted to do this properly, I would go back into these extrusions, into these sketches, and update these values to make sure that everything is all the correct definitions. So right now, this is using 10 millimeter value that's arbitrary, but it should be the thickness of the part. In this case, this is a unique bend radius. So I'm not necessarily worried about this one, but if I go back into my sketch here, this value should realistically be my bend radius. And so I should update this to utilize that value, and all I would have to do is come in here and tell it this is my defined bend radius. In order to keep the shape of the part the same definition that was here, I'm not going to modify that value. I am going to make this equal to the thickness though. All right, so now that I've done that, I'm going to try and create the flat pattern again, and there we go. So because I updated the radiuses in that bend to not have that thinning of the material, and I made them concentric or uniform thickness, the part was able to calculate where that continuation of the bends were, again, using that uniform thickness, and then repeat that throughout the design. So in this case, it was able to flatten it with no issues. Okay. Going back to the folded here, we can see our component is functioning. And if I were to go into my sheet metal defaults and adjust this value to say 11 millimeters, the whole part thickens without any errors in the creation of the part. It doesn't cause any weird behavioral problems with how it's making the design. And again, I took a minute, went through and updated all the sketches that referenced the thickness and tapped into the actual thickness parameter so that the sheet metal default values in this part were functional the way that we wanted them to be. So this was the left-hand version of this. I actually built this based on the right-hand version of this that I got from a SolidWorks user. So I'm simply going to go open up the IGES file that they sent over to me. And as I open up the IGES file, we are going to get presented with our standard importation option, right? We are going to convert this model to our design. I know that I've got a solid, so we're going to turn off all these options here. From here, I don't necessarily need to load the model because it is only one solid in the IGES, but there we can see the part that's going to come through. From here, I just want to make sure that it is in fact saving the file to the right location. And there's my part. Now this is a base solid. It doesn't have any features in it at all, right? Being an IGES, it won't. But just like I did before, I do want to just do a quick sanity check here and verify some dimensions. So I've got 10 mil for the base solid. The minimum distance here is 10 millimeters. So we know that that thickness is the same. We can restart and repeat this. And this is one of those things that I typically do when I get files of neutral format, is I'll go through and just kind of take some measurements and just see what the values are. That way I'm not surprised later when it doesn't work. I did import this using a standard part file template. So I do need to convert this to sheet metal. And just like before, when I hit that convert to sheet metal tool, it is going to be looking for me to define the thickness of this part. Now I did snap, a bunch of measurements and I know that it's 10 millimeters, but if I were to just click an open space here, or just hit enter or escape to get past this step, it basically didn't update the sheet metal thickness. So it thinks that it's still, the default value, which in my case is way too thin. So I'm going to uncheck that value. And then from here, I'm just going to enter in the definition that I'm after. If you, forget to do it, it's not the end of the world. You don't have to close the part out. You can always adjust this value to make it match. But again, this value and the thickness of the part, it's absolutely critical in order for this process to work. Now that I've done that, when I go to the define A side, this is another really good indicator that something is working properly. So when I did the define A side on my Inventor part that somebody modeled for me, I saw that this didn't trickle around. It didn't automatically wrap. And that pretty much told me that there was something wrong with it. But in this case, the A-side definition or the A-side calculation space is figuring out, okay, well, this is all continuous thickness throughout, so we're going to utilize that for our bend definition. And from here, I can now thicken this component. If I did want to change the thickness of this design, I can do it. It is a little bit of work, but it's typically not too bad. In this case, this solid is all continuous and it's using, straight linear bends. So I technically have an outer or inner quote unquote quilt that I can use to select for a feature. If I wanted to say make this part 8 millimeters thick instead, the first thing that I would want to do is on my 3D modeling tab, use my thicken offset command. And then from here, I can specify what faces I want to work with. But before I start picking objects, I definitely want to make sure to turn on the automatic face chain. In doing that, I can then select the faces of interest. And then from here, it's just a matter of updating that wall thickness inward or outward accordingly. So from here, I want to take 2 millimeters out of the thickness of this component. I can very easily come in and adjust that. In this case, subtract 2. It's then going to thicken the component. Basically, what this is worrying me about is that it's got some errors in the model. And what's happened is because I pulled that face in, my A side basically broke. So what I want to do here, we're going to just adjust the order of the operations here. And then recover this. And if I highlight the A side, you can see there that nothing highlighted. And that's basically what the error is showing. If I go back over to my sheet metal, I should be able to delete this. And put it there, delete. Oh, I know why. I still have a flat button. There we go. So now I can delete the A side, redefine it. And in here, you'll notice that it's essentially freaking out. And the reason it's freaking out is that my sheet metal defaults is the wrong value, right? The part thickness is 8 mil. This component is 10. So I need to make sure to adjust the thickness to match what I've set it to. and now the A side will function again. Now that I've done that, I can then tell it to create the flat pattern and it will generate properly. And that step of defining the A side is not absolutely critical. You don't have to do this step, but for generating bend notations and defining, especially for neutral components, it's really helpful to define this to make sure that it's kind of understood what face is the inner or outer face set. Inventor doesn't have, here nor there to work off of on a neutral solid, so it can really help. Now, when you make a model like this one, I started on this back face and extruded forward, so it kind of knows, where my orientation is to start from. But again, by defining it, I'm specifying exactly where I want the bend orientation to come from. Okay. So the last thing here that I want to work with is just how to handle components that may not have thickness at all. So in this case, I've actually created a AutoCAD file that is just surface geometry. And there are a lot of sheet metal fabrication software out there that they don't care about the thickness of that material, right? At the end of the day, it's, the inside and outside faces are fairly easily calculated based on one side. So in this instance in AutoCAD, I actually created this surface model. And the first thing you'll notice about this is, one, it's not super complicated, but it does have this giant bulbous lance in the middle of this shape, or this kind of stamp in the middle of this part. And because of that, this stamped section will not flatten as far as the Inventor is concerned. And that's fine, right? The important thing to note here is that all of the rest of the areas around it that do function in a linear deformation space, they will flatten, okay? So with that being said, I'm just going to close this file out. And over in Inventor, when I grab this file, I definitely need to make sure to tell it not to open the DWG file because I want to actually import it as a new part. So we're going to go to Options and switch it to Import. From here, I'm going to select that file to open it. On the wizard, it is an AutoCAD file, so I hit Next. The other thing that I did in the AutoCAD file is I made sure to erase out all of the stuff I don't need. In all reality, this is just the part. There was nothing else in this model whatsoever. There's not even any extra sketch lines or anything else. I cleared out all the riffraff. And the main reason for it is I don't want the importer to try to bring that stuff in when I don't need it. So from here, I need to specify what I'm working with. And in my case, in the AutoCAD file, I have surface data. So I'm going to tell it I need surfaces. I definitely want to tell that I need a new part file, not the default for new drawing. Right? I don't care about that. I did pick up that the files units were millimeters, so I don't have to change that. I did also change my part template because it's millimeters. I want the file to come in millimeters, so I just defined that as well. The rest of the options in here really don't matter, right? I don't need to worry about the constraint endpoints because it's surface geometry, not line stuff. I don't have any weird proxy objects in here, right? It's not mechanical or our AutoCAD architecture. It's just a standard simple surface. So from here, I can click Finish. Software's going to churn for a moment, and then I'm presented with my surface geometry from the AutoCAD space. If you're not familiar with surfaces inside of Inventor, it does give you essentially just an individual body. And then in this case, because of the import, it gave me an initial sketch. I actually don't need this. Surface bodies are split up based on what they are in the AutoCAD file. So I actually used a union operation on these objects in order to create one full surface. However, in AutoCAD, if I didn't do that step, I would need to come in here and use some very basic editing tools on this object in order to make it function as a single entry. Right? If it was multiple surfaces, it wouldn't necessarily work for my end goal. So I need to make sure they're all stitched together. And in the 3D modeling tab, there is a stitch tool in the surfacing model set. So there's the stitch command right there. But in this case, it came through, it's all one object, the surface one. So really all I need to do is make this a solid. And to do that, I'm going to use the 3D modeling thickened offset definition. In this case, I'm going to change the distance here to the thickness. And then from here, I just need to select my faces. And again, this is all continuous, so I'm going to tell it to automatic face chain. Now that I've done that, I can just simply rotate my view to make sure I'm thickening the right direction, which in my case, I want to go inward. I can then hit OK here, and it generates my component. Now in doing this, the surface is still there, and as I 3D rotate around this model, you kind of see it flickering on and off. So at this point, I just want to turn that visibility off in the model to get that out of the way. The other thing too is, for whatever reason, when the Inventor model imported the AutoCAD document, it applied this weird colorization to the parts. And I can change that if I were to go through and just select all those faces. I can come in and make them, the steel color, and that would clean up those surfaces. I'm not all that concerned about it, to be honest. I don't need to worry about modifying the coloring of this. It's still pretty well visible. My hunch says if I went into the AutoCAD file and checked the surface geometry that I created, it probably has that weird color associated to it, so I could fix it there. Then I don't have to fix it here, but it's kind of here or there. So back to my file here. As I mentioned, right, we know if I go to the define A side on this part, it's not going to work. And the reason it's not going to work is that this whole zone does not flatten. It won't flatten. And if you have a model like this that you're having issues getting it to flatten, but you have zones that should be uniform thickness and linear in deformation, you can hold the shift key down and select the areas you want to use as the backing for the flatten. And so in this case, I simply selected the outer flat surfaces that I want to create a flat pattern from. And once I have all those faces selected, I can then tell it to create the flat pattern. This usually takes a minute to figure out what it's doing. Well, let's try this one more time. I might need to save the file first. Interesting. It looks solid. I'm not certain what happened here. Let's try this real quick here. The other way that I can fix this or clean this up is to simply go in and remove that stamped zone from the model. So it didn't know the A side. I'm not sure why this file is crashing now. It literally just went through this. Okay, so you know where your bends are. Just trying to use that. All right, so let's do this. So we're going to clean up this surface and get rid of the that geometry. There's a couple of ways to do this. The first way is we need to remove these facets. So in this case, we're just going to use our standard delete face command. And in here, I'm just going to go through and select the half dozen faces that make up that stamped zone. And as I do that, it removes them. Now, obviously in this case, it left me with a hole. So I'm going to use the patch command and then simply patch that wound closed. Now that I have that, I'm now up to 2 surfaces. These are individual objects. So I need to stitch them together. And then using that stitch command, that will in turn close that up to make a continuous surface. Okay. Now that I've done that, I'll re-thicken the model. Let's edit the thicken. Just delete that out and redo it. Face chain, the thickness downward. And now that I've done that, I'll turn the A side back on, which in this case is damaged, so I'll recreate it. And now that I've got my A side, I can then create the flat pattern. So I'm not exactly certain why it failed the first time on creating it. It did work once before. It must have been something to do with the way that the geometry got imported on the second time around. But regardless of that, I know that I don't need that geometry at this point in the process in order to generate the flat pattern in this component. Additionally, if it is a true stamped operation, this flat pattern is probably not going to be accurate to the model anyway. It really just kind of depends on how your output files are going to play out. But you do always have access to the full editing functionality of Inventor. So if there are faces inside of that surface geometry or solid that are bad, you can always delete them out, recreate new ones, stitch all of that stuff together in order to recreate new surfaces that can then be used to thicken and generate your functional flat patternable component. So in this case, we went through a number of different instances. We started out using an existing 3D solid that was not sheet metal fabrication at all, and we used the corner and bend tools in order to clean up that object. We then looked at a neutral file or a bad modeled component that was supposed to be sheet metal. We went through and diagnosed some potential problems with it. In our case, we found that these edges were not uniform thickness through the bends. So we adjusted and fixed that and created a component that was then flattenable. We then imported an existing solid and then adjusted the thickness of the component, and then in turn adjusted the sheet metal defaults to make sure that they matched in order to keep the part flattening properly. And then lastly, we imported a surface geometry, used some editing tools on that surface geometry, thickened it to our sheet metal thickness, and then we're able to establish a new flat pattern out of that surface geometry. So a whole slew of different ways that we can work with Inventor geometry or geometry outside of Inventor in order to create functional sheet metal componentry. So at this point, I'd like to take a look at our questions, if there are any.
Keith, right now there have been 3 questions regarding flat pattern definition, specifying the A-side definition, which I believe I have answered to a point.
So once you have the A-side defined, you pretty much, the only way to get rid of it would be to delete the flat pattern, which obviously is going to have some pretty substantial repercussions on existing drawings and things like that. So, but if you did want to if you did have to flip it to say the back side of the component, the drawing would be invalid anyway. But yeah, you can delete the flat pattern, then delete the A side in order to recreate it. And as far as the criticality of it, it really only depends on neutral format files more than anything else. You know, obviously when you create a base extrusion or using the face command in sheet metal, you're defining the normal direction of the part, and that in turn is telling it the A side or the inside face versus the outside. But if you're working with like an imported object like this one or the IGES file, it has no way to define that, and it's going to just make its best guess. And if I want to have control over it, then I should definitely be picking, okay, this is the front or the A side model for, you know, calculations of neutral axis and bend orientation and angle. So more than anything else, it's just a matter of being in control of that data. But for standard operations, it's not absolutely critical to do that step. So it really just kind of is inversely related to the intelligence of the part, right? If it's a dumb solid, you definitely want to go through with it, go through defining the A side.
So far, that seems to be the only questions that have come in. Okay, here comes another one. I'm trying to use the corner seam function on an edge, but it won't allow me to select the edge. What should I look for?
So the first thing there that you would definitely want to make sure of is what method you're trying to work with. If you have a gap and you're trying to adjust the gap, you would want to use the seam side, where that would allow you to push and pull, you know, the gap between two edges. If you're trying to rip an edge, you have to select that option first. And then you can go through and select the hard edge of the part. It will offset, it'll rip away and offset back accordingly.
I don't see anything else coming in right now.
Excellent. Well, again, as Ashley mentioned in the beginning of the presentation, you will be getting a survey in your email, as well as, you know, an excellent place to insert additional questions. Would you use both when you are ripping and adjusting a seam width? It just depends on the process. If you've got already an existing seam in the part where you've got two, you know, pieces interacting, that corner seam tool can be used to adjust the seam's width of the gap size. You know, obviously right here you can adjust that spacing. if you don't have a gap at all, like in our first model, if there's a hard edge, at that point you can, again, you would want to use the rip method within this tool, and not the rip tool up here, which is really meant for like selecting two faces or points on a face to remove them. This is meant to remove edges of a part and offset them.
And I would like to add to what you pointed out earlier, want to stress this, the order of operations when using corner bends and corner rips heavily depends on that model geometry and which one you do first and second. So if it's not working out in one particular way, definitely back up and switch some things around.
Yeah. The way that I've had the cleanest success using the corner seam and the bend tools is rip all the geometry you need using the corner seam rip option and get rid of all the edges you're not going to want, including areas that you're going to reestablish new bends. And the idea behind it is if you rip it all away, when you use the bend tool, it's going to have clean edges to apply its end treatments accordingly. And that usually gives me the cleanest corners of where those bends exist. Then anywhere that you have an area or an edge that needs a bend and doesn't have one, use the bend tool to apply them. Then go back in and add any superficial bends to the component. And if I go back over to that hood main component here, the general idea is, in all reality, this bend and that bend, if I wanted to move their positions to be somewhere else, for example, I can grab these and delete those features and then reapply a new bend, say between here and here, and then cut that bend back. I'll repeat it on the other side. Now my corner treatments are kind of ripping these up a little bit, but I could go fix that at any time. But because of the order of operations, I can easily go in and adjust. Okay, well, I don't want that T shape to be so large. And so I can go in and make that cleanup as necessary.
And don't be afraid to incorporate the standard modeling tools like extrude to perform cut operations to remove certain things. There is a cut command in the sheet metal tools, but every once in a while you run into that really weird, really unique situation where maybe the sheet metal tool isn't quite getting you to the finish line that you wanted. You can incorporate some of the standard modeling tools. You just got to make sure to not invoke any changes on that sheet metal thickness. I don't see any other questions coming in.
Excellent. Well, like I said, if you do have any other questions that come up in the future, don't hesitate to reach out via your don't hesitate to reach out to your salesperson or to us at Service at Heckman if you have our service contract. Yeah, Ashley, if you have any other final parting thoughts.
Well, I'll just thank everyone for attending and thank you for the presentation. And thanks to Kindred for sitting in, and I hope you all have a great day. We'll see you next time.